Good day everyone, this is the module 2 of Operations Research 1. So this is about the linear programming of process mix with more than 2 constraints. So this includes the algebraic solution, graphical solution, and the simplex algorithm. So the duration of this module is 3 weeks. So from the previous module, the discussion is focused on solving product mix with linear programming problems using algebraic solution, graphical, and simplex algorithm, as well as the Excel solver. In the second module, same methods will be used, but the linear programming problems involved are process mix with more than 2 constraints. Okay, so the objectives of this module, after careful study of this module, you should be able to do the following. First, be able to solve maximization, minimization, LP problems, process mix with more than 2 constraints with algebraic solution, graphical solution, simplex algorithm, as well as the Excel solver add-ins. So the pretest here is just the same with the pretest in the first module. So you can start answering this by commenting on the post in our Google Classroom. Next, for the lesson proper, maximization or minimization of LP problems, process mix with more than 2 variables. 1.0, the algebraic solution. So for example 1, we have a new problem here. A feed milling company is operating with 3 main processes: material preparation, MP, feed milling operation, FMO, and delivery, D. The company has set a target to prepare 60 tons or less of mixed ingredients, 120 tons or less of finished product, and at least 10 tons of delivered finished product per day. Okay? So MP includes 1 machine and 3 workers. FMO includes 3 machines and 4 workers. And D includes 1 machine and no workers because the workers are outsourced or being hired from other company. If it is estimated that for every 1 worker, 3 tons of finished product is to be made, while 5 tons of finished product is to be made for every 1 machine. Formulate the linear programming model specifying the process mix which will maximize the output satisfying the target. Okay? So for the answer, first we will let the unknowns. Okay? So let x sub 1 be the number of manpower. Then x sub 2 be the number of machines. So the objective function to establish in order to maximize the output. So it is maximization because it is stated here in the problem, maximize the output. Okay? So the output in tons per number of manpower and machine is, so let z is equal to the optimal value. So this is the objective function. So z is equal to 3x sub 1 because we are going to maximize 3 tons per number of manpower. Okay? Plus 5x sub 2 because we are going to maximize 5 tons per number of machines. Okay? Next, since MP includes 1 machine and 3 manpower with a target of 60 tons or less mixed ingredients, the first constraint can be expressed as, okay, like this. Okay, so 1 machine plus 3 manpower. Okay, it is less than or equal to 60 tons. Similarly, for constraint 2 and 3, okay, we have 3x sub 1 plus 4x sub 2 less than or equal to 120. So how do we get this? This 3x sub 1, this constraint is from FMO. While this constraint, x sub 1 greater than equal to 10 is from D or the delivery. Okay? So we also have the non-negativity constraint. So x sub 1, x sub 2 are greater than or equal to 0. So that is our linear programming model. So step 1, first we convert the inequalities from the constraints, okay, to equations. So you already know how to convert them, okay? You will just add slack variables. Since it is maximization and the inequality sign is less than equal, we will use positive slack variables, okay? So here there will be a negative slack variable. Why? Because of the sign greater than equal, okay? So we have also done a negativity constraint. The slack variables must be greater than or equal to 0 also. So for the step 2, solve using algebraic method. So computation for the solution and objective function. Okay? So between C sub 1 and C sub 2, if x sub 3 and x sub 4 is equal to 0, then we can use elimination method. Okay? So you notice that this is the first constraint. You can substitute this to constraint 1 or constraint 2. But here, it is substituted to constraint 1. Okay? So you substitute it here because this is x sub 2 and x sub 4 or x sub 3 here is 0. Okay? So you simplify, you get the x sub 1, which is 24. Now to get the x sub 5 here, you just substitute the value of x sub 1 in the third constraint. Okay? So it is 24. Okay? Then simplify. Transpose, this will be negative 14. Since this negative x sub 5 has negative, it will be positive 14. Okay? So all the variables here are positive. So this is feasible. You will compute for the optimal z. So you just substitute them in the equation to this converted equation. Okay? So 3 multiplied by x sub 1, which is 24, plus 5 multiplied by 12, okay, because x sub 2 is 12, plus 0 times 0, plus 0 times 0, plus 0 times 14, because x sub 5 is 14. So you get 132, okay, as the optimal z value between in this computation. Next, computation under algebraic method between C sub 1 and C sub 3. So here we will just use two constraints at a time. So this first equation is the C sub 1 and this second equation is the C sub 3. Okay, so this 0 is x sub 5 because x sub 5 here is 0. That's why you get x sub 1 here, okay, which is 10. Now, you just substitute this 10 to this equation, okay, to get x sub 2. So by substituting that, it will be like this, okay. So you have x sub 2 is equal to 50 over 3, okay. Now you substitute them to the second constraint to get x sub 4. So x sub 1 is 10, then x sub 2 is 50 over 3, okay. Then simplify. You get x sub 4 is equal to 70 over 30. So, since all the variables here are positive, you will compute for the z value. So, 3 multiplied by 10 because 10 is x sub 1. 5 multiplied by 50 over 3 because x sub 2 is 50 over 3. And 0 multiplied by 0 because x sub 3 is 0. 0 multiplied by 70 over 3 because x sub 4 is 70 over 3. Plus 0 multiplied by 0 because x sub 5 is 0. So you get this 340 over 3 or 113.33. Okay? So next, between C sub 2 and C sub 3, so you will just pair every constraint. Okay? And you notice that we let the slack variables to 0. First, in the first computation, we let x sub 3 and x sub 4 equals to 0. Second, x sub 3, x sub 5 equals to 0. Then in the third, x sub 4 and x sub 5. So this last variable, you will just let them to 0. Okay? So then, this is the second constraint, okay? This is 0 because x sub 4 is 0. Now this is the third constraint, okay? So this is 0 because x sub 5 is 0. So now you have x sub 1 is equal to 10. You just substitute this 10 to this equation, the constraint 2, okay? To get x sub 2. So by substituting it here, you get x sub 2 is equal to 90 over 4. Okay? Then substitute x sub 1 and x sub 2 value to the first equation, which is here. Okay? So x sub 1 is 10, then x sub 2 is 90 over 4. So you get x sub 3 is equal to negative 70 over 4. So there is a negative variable. This solution is infeasible because one of the variable is negative. So we will not solve for z. Okay? Then you can state your conclusion. The company should add 24 workers, okay, and 12 machines. So why do we choose 24 workers and 12 machines? Because we are maximizing the problem. We get the highest optimal z with 132, and it corresponds to this variable x sub 2 12, x sub 1 24, x sub 5 14. Okay, that's why we get them. So the company should add 24 workers and 12 machines in their operation to have an optimal output of 132 tons of finished products. Okay, so you will not add this x sub 5 equals 14 to your conclusion because the slack variables do not affect the value of optimal z. Okay, next, for example number 2, a firm manufactures fishing tackles. Among all of its products, 3 products are subjected into a study: the baits, floats, and hooks. The management wants to minimize the number of rejects per crate of the finished products. So this is a minimization problem. The firm is operating with 2 production lines, P1 and P2. It takes 5 hours to finish 1 crate of baits in P1, while 1 hour in P2. It takes 1 hour to finish 1 crate of floats, both in P1 and P2. And it takes 1 hour to finish 1 crate of hooks in P1, while 4 hours in P2. On a day, the total time available for bait production is at least 10 hours. At least 6 hours for float production, and at least 12 hours for hooks production. The average number of reject per crate of finished products that are incurred in P1 is 3, while in P2 is 2. Okay? So for the answer, we will let again the unknown variable by x sub 1 be the number of crates produced in P1, or the production line 1. Then x sub 2 be the number of crates produced in production line 2, or P2. So the objective function to establish in order to minimize the number of rejects per crate, because here we want to minimize the number of rejects per crate produced in P1 and P2, is z is equal to 3x sub 1, because the average reject per crate of finished product in P1 is 3, and x sub 1 is number of crates produced in P1, plus 2, okay, and x sub 2 is the number of crates produced in P2. So this is your objective function that you want to minimize. So next, since it takes 5 hours to make 1 crate of baits in P1, while it takes only 1 hour to make the same product in P2, with the total time available for bait production of at least 10 hours a day, the first constraint can be expressed as this. Okay? So 5 hours for x sub 1, which is in P1, then 1 hour for x sub 2, which is in P2. So they are greater than or equal to 10, because this is it is said in the problem that at least 10. Okay? Similarly, for constraint 2 and 3, this will result. Okay? So you just refer to the problem why this constraint have the coefficient 1, 1. Okay? So it is in the problem. Next, additionally, since there is no negative number of crates, okay, the following non-negativity constraints are concluded. So we have also a non-negativity constraint. Okay? Next, hence the process mix problem in linear programming model is as follows. We are minimizing the objective function z is equal to 3x sub 1 plus 2x sub 2, subject to these constraints. 5x sub 1 plus x sub 2 greater than equal 10, x sub 1 plus x sub 2 greater than equal 6, x sub 1 plus 4x sub 2 greater than equal 12, x sub 1, x sub 2 greater than equal 0. So for the first step, we convert the inequalities, okay, to form from the constraints to equations. So you already know that how to convert them. You will just add the slacks variable. And you notice that the slacks variable here, x sub 3, x sub 4, and x sub 5 are all negative because of the sign of the inequality here, which are greater than equal. Okay, so also the negativity constraint. They all the variables must be greater than equal to 0. To solve using algebraic method, so between constraint 1 and constraint 2, if x sub 3 and x sub 4 is equal to 0, then we will just use the elimination method. So you notice here that this is the first constraint, okay? And this is the second constraint. So to have the elimination method, we multiplied negative 1 to the first constraint to eliminate x sub 2, okay? Because negative x sub 2 plus x sub 2 is 0. So you only have x sub 1. So negative 5x sub 1 plus x sub 1 is negative 4x sub 1. Then here, negative 10 plus 6 is negative 4. So negative 4 divided by negative 4 is positive 1. So you have the value of x sub 1, which is positive 1. Now substitute this value to any of the constraints to get any of the constraints between c sub 1 and c sub 2 to get the value of x sub 2. So here we use the constraint 2. So by substituting x sub 1, which is 1 here, we get the value of x sub 2 is equal to 5. Then just substitute these values to the third constraint. Okay? So you get x sub 5 is equal to 9. So since all the variables, resulting variables are positive, we will compute for the z value. So 3 multiplied by 1 because x sub 1 is 1 plus 2 multiplied by 5 because x sub 2 is 5 plus 0 multiplied by 0 because x sub 3 is 0 and 0 multiplied by 0 because x sub 4 is 0 plus 0 multiplied by 9 because x sub 5 is 9. So it is equal to 13. Now for the number 2 computation between constraint 1 and constraint 3. So if x sub 3 and x sub 5 is equal to 0. Okay? Then you notice here that this is the first constraint and this is the third constraint. So we just multiply negative 4 to the first constraint to eliminate x sub 2. Okay? Because negative 4x sub 2 plus positive 4x sub 2 is equal to 0. So what is left here is negative 20x sub 1 plus x sub 1 is equal to negative 19x sub 1 equals to negative 40 plus 12 is negative 28. So simplifying, we get x sub 1 is equal to 28 over 19. So we just substitute this value of x sub 1 to any of the constraint c sub 1 or c sub 3. So we use the c sub 1 here. So this is the value of x sub 1. So simplifying, we get the value of x sub 2, which is 50 over 19. Next, we just substitute the two values, the x sub 1 value and the x sub 2 values, to the second constraint. Okay, so this is x sub 1, this is x sub 2. So we get the value of for x sub 4 is negative 36 over 19. So the solution is infeasible because one of the variables is negative, which is x sub 4. So we will not compute for z. Next, number 3, between constraint 2 and constraint 3. If x sub 4, x sub 5 is equal to 0. So you notice that this is the second constraint and this is the third constraint. We just multiply negative 1 to the second constraint to eliminate x sub 1, okay? Because negative x sub 1 plus positive x sub 1 is equal to 0. So what is left here is x sub 2. So negative x sub 2 plus positive 4x sub 2 is equal to positive 3x sub 2. So it is being shortcut here, okay? Because if in this corner is positive 3x sub 2 and in this corner it is positive 6, so 6 divided by 3 is 2. So we have x sub 2 is equal to 2, okay? Then just substitute the value of x sub 2 to the second constraint, okay? So since x sub 4 is 0, okay, you can get x sub 1, which is 4. Now just substitute the two values, x sub 2 and x sub 1, to the first constraint. So simplifying, we got x sub 3 is equal to 12. So all the variables are positive, so we can compute for the z value. So to compute that, this is 4 because x sub 1 is 4. Then this is 2 because x sub 2 is 2. Then this is 12 because x sub 3 is 12. So 0, 0. So it is equal to 16. Okay? So now you can state your conclusion. The firm should produce 1 crate of each finished product in P1 and 5 crates of each finished product in P2 to minimize the number of rejects to 13 pieces per crate. So we chose this, okay, because we are minimizing here. So the lowest value is 13. That's why we chose the solutions here. Okay, just we ignore the value of x sub 5. So that's it. Next, for the graphical solution. So this method is used to solve two variables, okay, because we have x and y. So the example 1, just copy paste the linear programming model here. Then step 1, represent the constraints with a graph, okay? Since x sub 1 and x sub 2 are greater than 0, we will just use the first quadrant. And x-axis represent x sub 1 and y-axis represent x sub 2. Okay, for constraint 1, we will just let the other variable to 0 so that we can get the other variable. Okay, so in constraint 1, if x sub 2 is 0, then we get x sub 1 as 60. So you can plot in your graph the coordinate 60 and 0. Next, for the y-axis, if x sub 1 is 0, then x sub 2 is 20. So you can plot 0, 20 to the y-axis of your constraint 1. Then connect these two to have a graph. Okay? Then just do the same with constraint 2 and constraint 3. But here in constraint 3, there is no x sub 2. Thus, it may take 0, 0 to infinity, infinity. Okay? Because there is no given x sub 2. Only x sub 1. So this is x sub 1 only. Okay? There is no 1 here. So plot this 10, 0 along the x-axis of constraint 3. So the resulting graph is looks like this. Okay? So this is the constraint 1, this is the constraint 2, and this is the constraint 3. Okay? So step 2, shade the feasible region, the collection of feasible solution for which all the constraints are satisfied. So you already know the feasible region, okay? Because we have discussed it in module 1. Since the inequality sign in C sub 1 and C sub 2 is less than or equal, okay, less than or equal, and the inequality sign in C sub 3 is greater than or equal, okay, the feasible region should include the left side of each line C sub 1 and C sub 2. That's why it is here, the left side of C sub 1, the left side of C sub 2, and the right side of C sub 3, satisfying all constraints. So this is C sub 3, the right side is this. Okay, so we have the feasible region here. Okay, this is the shaded part, satisfying all the constraints. So to find the coordinates of the corner or the corner point feasible CPF solutions, because they are the points dominating all points in the feasible region. So for point A, we have 10 and 0. Okay, so 10x sub 1 and 0x sub 2. So for point B, by substitution, because this is the constraint 1, okay, and this is the constraint 3, you will just substitute constraint 3 to the x sub 1. Okay, so substituting, you get 50 over 3. Okay, so in point B, you have the coordinates 10 x sub 1 and 50 over 3 for x sub 2. Okay, okay, so for letter C, it is by elimination method. So it is between the constraint 1 and constraint 2 because they are the ones who intersect with each other. So you notice that this is the constraint 1 and this is the constraint 2. We just multiply the constraint 1 with negative 3 for us to eliminate the first term, because negative 3x sub 1 plus positive 3x sub 1 is 0. So what is left is x sub 2. So negative 9x sub 2 plus 4x sub 2 is equal to negative 5x sub 2. So it is being shortcut here. Okay, so here negative 180 minus positive 120 is negative 50. So negative 50 divided by negative 5 is equal to positive 12. That's why x sub 2 is positive 12. So now just substitute to the first equation, the x sub 2. So x sub 1, you get the x sub 1 of 24. So you have these coordinates in the intersection, which is 24 and 12. Okay, and for point D, so it is here. It is 40 x sub 1 and 0 x sub 2. Okay, so here the graph is labeled with the coordinates. Step 4, find the optimal solution by substituting the values of x sub 1, x sub 2 to the objective function. Okay, for point A, substitute it here. So you get 30. For point B, substitute the solutions to the equations. So you get this. For point C, substitute these solutions to this. You get this. And for point D, substitute this solution to the equation. So you get this. So since we are maximizing here, we get the highest, which is 132. So this color green font is our optimal solution. So the conclusion is just the same with the above conclusion in the algebraic method. Okay. Next, for the example 2, just copy paste the LP model. So minimization. For step 1, represent the constraint with the graph. So it is just the same with the minimization. So you will let one variable equal to 0 to get the another variable, so that you can plot these coordinates and connect them. You have a graph of each constraint. Okay, so your graph should be like this. This is the constraint 1, this is the constraint 2, and this is the constraint 3. Now step 2, shade the feasible region. Since the inequality sign for C sub 1, C sub 2, and C sub 3 is greater than or equal, okay, the feasible region should include the right side of each line, C sub 1, C sub 2, and C sub 3, satisfying all constraints. That's why the feasible region should be like this. All the shaded parts are on the right side of all the graph of the constraints. Okay. So now finding the coordinates of the CPF solutions. For point A here, you got 0 for x sub 1 and 10 for x sub 2. And for point B here, it's through elimination method between the constraint 1 and the constraint 2. So you notice that this is the constraint 1 and this is the constraint 2. Okay? So we just multiply negative 1 to the constraint 2 to eliminate the second term. Okay? So what is left is this. Negative 5x sub 1 plus positive 5x sub 1 plus negative x sub 1 is equal to positive 4x sub 1. Next, 10 plus negative 6 is positive 4. So 4 divided by 4 is 1. So we have x sub 1 is equal to 1. Now substitute this to the first equation. So substituting, you get x sub 2 is equal to 5. Okay? So for point B, you have the coordinates 1 for x sub 1 and 5 for x sub 2. Next, for point C, it is elimination method again between constraint 2 and constraint 3. Okay? So this is constraint 2, this is constraint 3. So you notice that we multiply negative 1 in the constraint 2 to eliminate the first term. Now what is left is this. Negative x sub 2 plus 4x sub 2 is positive 3x sub 2. Next, negative 6 plus positive 12 is 6. So you have your value of x sub 2 equals to 2. So substitute this value to the first equation. You will get x sub 1 is equal to 4. Thus, the coordinates for point C is 4 and 2. Now for the point D, so it is here. You have 12 for x sub 1 and 0 for x sub 2. So you should put those coordinates along with the points. Then step 4, find the optimal solution by substituting the values of x sub 1 to the objective function. Okay, for letter A, you substitute the solutions to the objective function. You get 20. For B, you get 13. For C, you get 16. For D, you get 24. So since we are minimizing here, we will choose the lowest value, which is 13. Okay? Lowest positive value. So that is our optimal Z. So the conclusion is the same with the above conclusion for the algebraic method. Next, 3.0, the simplex algorithm. So from the example number 1 problem, just copy paste the LP model here. For step 1, create a simplex table. Multiply the third constraint with negative 1 to get an identity matrix. Okay? That is encircled here. So begin with x sub 3, x sub 4, and x sub 5 as the basic variables. Here, they are under x sub b, or the basic variables, while x sub 1 and x sub 2 as the non-basic variables. So here, just multiply negative 1 to the constraint 3, okay, to make this positive 1, so that you have an identity matrix to start. So, step 2, having a negative value in RHS means that the primal simplex problem is infeasible. So instead of choosing the column with the highest positive value of Cj minus Zj, choose the least, which is 3. Okay? So this is done if you have a negative value here in the RHS. You will choose the lowest positive here. Okay? So if there is a negative value, it shall be selected first. Okay? So if there is a negative value here in the Cj minus Zj, it should be selected here. Okay? So this is called the dual simplex way. So this way of solving the simplex is called the dual simplex. So then choose the RHS value with the negative sign. Okay? So we will choose negative 10. Thus, x sub 5, this row x sub 5, okay, is to be replaced by column x sub 1. Okay? So again, add rows from the previous table to make the second iteration. Okay? So replace x sub 5 by x sub 1 through using the pivot, which is the intersection of x sub 1 and x sub 5. So what is it? It is negative 1. Okay? Because it is in the intersection of row x sub 5 and column x sub 1. So divide the pivot by row by 8. Okay? To rewrite. So to replace x sub 5 here by x sub 1, just divide these elements by the pivot element, which is negative 1. So negative 1 divided by negative 1 is 1. 0 divided by negative 1 is 0. 0 divided by negative 1 is 0. 0 divided by negative 1, 0. 1 divided by negative 1 is negative 1. Negative 10 divided by negative 1 is positive 10. Okay? So now we will rewrite row x sub 3 and x sub 4. So to rewrite them, we should make a identity matrix between x sub 3, x sub 4, and x sub 1. Okay? So you notice that here, value of 1, x sub 1, the elements here, under the row of x sub 1 is 1. 1 x sub 4 and x sub 0 are 0, 0. Okay? So under x sub 3 should be like this. 1, 0, 0. And under x sub 4 should be like this. 0, 1, 0. To have a identity matrix. Okay? So you think of a number that you can use to make these values. So for x sub 3, it should be 1. Okay? Because when we multiply 1 times 1 is equal to 1, then we minus the previous value 1 with 1 is equal to 0. Okay? Then 0 times 1 is 0. So 3, the previous value minus 0 is 3. Okay? Then 0, so just copy paste the 1, 0, just copy paste 0. Okay? Then negative 1 times 1 is negative 1. So the original value is 0. So 0 minus negative 1 is positive 1. Okay? So next, 10 times 1 is 10. So 60 is the original value. So 60 minus 10 is 50. Okay? Now for x sub 4. So the value that should be used here is 3. Because when we multiply 1 by 3, so it is equal to 3. So the original value is 3. So 3 minus 3 is equal to 0. Okay? Next, 0. So just copy paste the original value for 0 again. Just copy paste 0. 0 again. Just copy paste 1. Now, 3 multiplied by negative 1 is equal to negative 3. So the original value is 0. 0 minus negative 3 is positive 3. Next, 3 times 10 is 30. So the original value is 120. So 120 minus 30 is 90. Okay? Do you get it? How do we rewrite x sub 3 and x sub 4? So now, we will compute for the value of Cj minus Zj. Okay? So the numerical coefficient in the objective function of x sub 3 is 0, x sub 4 is 0, and x sub 1 is 3. Okay? So 0 times 0, 0 times 0, okay? Then 3 times 1 equals to 3. So the numerical coefficient of the column here is 3. So we will minus it with this. So 3 minus 3 is equal to 0. Okay? So next, 0 multiplied by 3, 0 multiplied by 4, then 3 multiplied by 0. So we just copy paste 5, okay? Because they are all 0. Next, 0 multiplied by 1, 0 multiplied by 0, 3 multiplied by 0. So we just copy paste 0. And 0 multiplied by 0, 0 multiplied by 1, 3 multiplied by 0, just copy paste 0. Then 0 multiplied by 1, 0 multiplied by 3, and 3 multiplied by negative 1. So it is negative 3. So 0 minus negative 3 is positive 3. So next for the RHS, 0 times 50, 0 times 90, so 3 times 10 is 30. Okay? Now, since there is no negative sign here in the RHS, we can now proceed through the simplex way. Okay? Because all the values here on the RHS are positive. We will now adhere to the ways of a simplex way. Okay? So, based on the simplex way, we will choose the highest value of Cj minus Zj, okay? Which is 5. That's why this is our denominator for the theta, 3, 4, and 0, okay? So, 50 divided by 3 is equal to 50 over 3. Then, 90 divided by 4 is equal to 90 over 4. Then, 10 divided by 0 is undefined. So, for the third iteration, okay, so we will choose to enter x sub 2, okay, because it has the highest Cj minus Zj in the second iteration, and it will be replacing x sub 3, okay, because it has the lowest value of theta. So 50 over 3 is lower than 90 over 4, okay. So the pivot element here is, or the intersection here is 3. So we will just divide all the elements, the previous elements of x sub 3 with the pivot element 3 to change it with x sub 2. Okay? So 0 divided by 3 is 0. 3 divided by 3 is 1. 1 divided by 3 is 1/3. 0 divided by 3 is 0. 1 divided by 3 is 1/3. 50 divided by 3 is 50 over 3. Okay? So now, we will think of a number that will make a identity matrix between x sub 2, x sub 4, and x sub 1. So for x sub 4, this value should be 0 because we have the value of 1 here for x sub 2. So to obtain that, we will choose number 4. Okay, so 4 times 1 is 4. Then we will subtract it from the original value, which is 4. So 4 minus 4 is 0. Okay? So in this first, it is just 0. So 0 times 4 is 0. Then 0 minus 0 is 0. Okay? Next, 1/3 times 4 is 4/3. So the previous value is 0. So 0 minus 4/3 is negative 4/3. Okay? Now, next, this is 0. So just copy paste the original value, which is 1. Next, 1/3 times 4 is 4/3. So the original value is 3. So 3 minus 4/3 is equal to 5/3. Okay? So next, 50 over 3 multiplied by 4 is 200 over 3. So the original value is 90. So 90 minus 200 over 3 is equal to 70 over 3. Okay? So now for x sub 1, what is the value that will make the identity matrix? So this element should be equals to 0, as well as with this element. Okay? So to get those values equal to 0, we will just use the number 0 to multiply in the row of x sub 2. Okay? So if we use 0, then we will just copy paste the original elements, which is 1, 0, 0, 0, negative 1, and 10. Okay? So now we are ready to compute for the Cj minus Zj. Okay? So for the first one, 5 times 0 is 0. 0 times 0, 0. 3 times 1 is 3. So 3 minus 3 is 0. Okay? 5 times 1 is 5. 0 times 0, then 3 times 0. So we have 5 here. So 5 minus 5 is 0. Okay? Next, 5 times 1/3 is 5/3. 0 times negative 4/3 is 0. 3 times 0 is 0. So we only have 5/3. So 0 minus 5/3 is negative 5/3. Next, 5 times 0, 0 times 1, 3 times 0. So just copy paste the 0 here. Next, 5 times 1/3 is equal to 5/3. 0 times 5/3 is equal to 0. So 3 times negative 1 is negative 3. So 5/3 plus negative 3 is equal to negative 4/3. So we will subtract it here. So 0 minus negative 4/3 is equal to positive 4/3. Since all the values in the RHS are positive, we will adhere to the simplex way again. Okay? We will choose the highest positive value, so which is 4/3 under column x sub 5. Okay? Then we will choose the lowest value of theta, which is 14 along the row of x sub 4. So x sub 4 will be replaced by x sub 5. Okay? Because when we divide 50 over 3 by 1/3, we got 50, and we divide 70 over 3 by 5 over 3, we get 14. Then when we divide 10 with -1, do not evaluate. Okay, so because if the theta is negative, we shall not evaluate it. Okay, so now for the fourth iteration, x sub 4 is replaced by x sub 5. Okay, so how do we replace it again? We determine the pivot. So from third iteration, the pivot is 5/3. Okay, because it is in the intersection of x sub 4 and x sub 5. Okay, so we will divide each elements by 5/3. So 0 divided by 5/3 is 0. 0 divided by 5/3 is 0. So negative 4/3 divided by 5/3 is equal to negative 4/5. Then 1 divided by 5/3 is equal to 3/5. 5/3 divided by 5/3 is 1. 7 over 3 is equal to, or 7 over 3 divided by 5/3 is equal to 14. Okay, so next, think of a number to rewrite row x sub 2 and x sub 1 that will form a identity matrix. Okay, for x sub 2, this value should be 0, okay, to have an identity matrix. So what number is to be used here? So we will use 1/3, okay, because when we multiply 1/3 by 1, it is equal to 1/3. Then we will subtract it with the original value. So 1/3 minus 1/3 is equal to 0. Okay, so you will do that for the rest. 0, so since this 0, just copy paste the original ones. So 0 and 1. Now here, negative 4/5 times 1/3 is equal to negative 4/15. So we will subtract it from the original value, which is 1/3. So 1/3 minus negative 4/15 is equal to positive 9/15. 9 over 15. Okay? So next, 1/3 times 3/5 is equal to 3/15. Okay? So 0 minus 3/15 is negative 3/15. So 14 times 1/3 is equal to 14/3. Okay? So we will subtract it from the original. 50/3 minus 14/3 is equal to 12. Now for x sub 1, what value shall we use to make a identity matrix? So the value of this element should be 0. So what number should we use to make it 0? So we can use -1, because 1 multiplied by -1 is equal to -1. Okay? Then we will subtract it from the original value, which is -1. So -1 minus -1 will be equals to 0. Okay? So you will do it for the rest. So since there are two zeros here, you will just copy paste the original value, which is 1 and 0. Next, negative 4/5 times -1 is equal to positive 4/5. So the original value is 0, so positive 0 minus 4/5 is equal to negative 4/5. So next, 3/5 times -1 is equal to negative 3/5. So subtract it from the original, which is 0. 0 minus 3/5 is equal to, or 0 minus negative 3/5 is equal to positive 3/5. Okay? Next here, 14 times -1 is negative 14. Then we should subtract it from the original value, which is 10. So 10 minus negative 14 is equal to positive 24. So since the value of basic variables x sub 1, x sub 2, and x sub 5, okay, so this value of cj minus zj under the column of x sub 1, x sub 2, and x sub 5 are equal to 0, and the values of the non-basic variables, which are under this column, x sub 3 and x sub 4, are negative values, no variable can be entered anymore. Thus, the algorithm terminates, giving the best solution. So, the best solution here is 24 for x sub 1, okay, and 12 for x sub 2. And their best optimal value is 132, because when we multiply 5 by 12, it is equal to 60, and 0 by 14 is 0, then 3 times 24 is 72, so 72 plus 60 is 132, okay? So the solution value of x sub 5 does not contribute to the objective function because it has the coefficient of 0, okay? So now for that tabular form minimization, so minimize this subject to, so just copy paste the model for minimization, problem 2. So step 1, to start a simplex minimization table, you will add artificial slack variables and artificial variables, okay? And this big M, okay, notation. So you already know this in the previous module because you did this also in the previous module. So all these slack variables are negative because of the greater than equal sign of the constraints. So there is also a non-negativity constraint, okay? So all variables must be greater than or equal to 0. So for the step 2, make a simplex table, okay? Then since this is minimization simplex, you multiply the objective function values with -1, okay? That's why all values here are multiplied by -1, okay? So notice that there is matrix with identity property. So what is the matrix? Matrix that has the identity property between a sub 1, a sub 2, and a sub 3. So this is it, okay? So that will serve as the starting solution. Okay, so we will just leave the Cj minus Zj value of RHS, okay, this is it, to triple dash until there is no artificial variable in the solution. So until there is no M here, okay, or there is no A variables here, okay, in the solution. So step 3, choose to enter x sub 1 with the highest positive value of Cj minus Zj, okay, because it has the highest positive value. So we will choose the highest positive value because all the variables in the RHS are positive, okay. Then we will replace a sub 1 because it has the smallest value of theta, which is 2. So when we compute the theta, 10 divided by 5 is 2, 6 divided by 1 is 6, 12 divided by 1 is 12. So the slowest is 2. So a sub 1 will be replaced by x sub 1, okay, and the pivot element or the intersection element is 5, okay. So we will use it to replace a sub 1 with x sub 1. So divide all the elements here with 5, with the pivot element. So 5 divided by 5 is 1. So this is for second iteration, okay. So 1 divided by 5 is 1/5. -1 divided by 5 is -1/5. 0 divided by 5 is 0, 0, 0. So 1 divided by 5 is 1/5. 0, 0, 0. Okay. So next, 10 divided by 5 is 2. Okay. So now think of a number that you can use to make an identity matrix while rewriting a sub 2 and a sub 3. So the value of a sub 2 here should be 0. Okay. So the number we can use is 1 because when we multiply 1 with 1 is equal to 1. So we subtract it from the previous value, which is 1. So 1 minus 1 is equal to 0. Okay. So next, we multiply 1/5 by 1 is 1/5. Then we subtract it from the original value, which is 1. So 1 minus 1/5 is equal to 4/5. Next, negative 1/5 is times 1 is equal to negative 1/5. Then we subtract from the original value 0. So 0 minus negative 1/5 is equal to positive 1/5. Okay? Next. So this is 0. So just copy paste the original value. 0, copy paste the original value. Then 1/5. So 1/5 times 1 is 1/5. Then subtract here in the original, which is 0. So it will be negative 1/5. Next. 0, just copy the original. 0, just copy the original. Okay? Next, 2 times 1 is 2. Then subtract from the original, which is 6. So 6 minus 2 is 4. Okay? Now, for a sub 3, what number should we use to make an identity matrix? So it is also 1, because when we multiply 1 by 1 and subtract it from the original value, which is 1, it is equal to 0. Okay? So next, 1 times 1/5 is 1/5. So 4 minus 1/5 is equal to 19 over 5. Next, negative 1/5 times 1 is negative 1/5. So subtract it from the original, which is 0. So it will be positive 1/5. So next, since these are zeros, just copy paste the original values. Then 1/5 times 1 is 1/5. Subtract it from the original, then it will be negative 1/5. Then, since these are zeros, just copy the original values. Okay. Next, 1 times 2 is 2. Then subtract from the original, which is 12. So it will be 10. Okay. So now we will compute the Cj minus Zj. So negative 3 times 1 is negative 3. So these two are zeros. Okay. So the numerical coefficient here is negative 3. So negative 3 minus negative 3 is equal to 0. So next, column x sub 2. Negative 3 times 1/5 is equal to negative 3/5. Okay. Then we will add it to negative 4/5 m and negative 19th m. Okay. Then the sum will be subtracted from the numerical coefficient here, which is negative 2. So the resulting value is 23 over 5m, okay, minus 7/5. Okay. So next, negative 3 multiplied by negative 1/5 is positive 3/5. So add it to negative 1/5 m and negative 1/5 m. Okay. So when you add it, the sum, you will use the sum to subtract from the numerical coefficient here. So what is the numerical coefficient here? This is x sub 3, so it is 0. So the resulting number is 2 over 5m minus 3/5. Okay. Next, for the column of x sub 4. So for the column of x sub 4, negative 3 multiplied by 0 is 0. Negative m multiplied by negative 1 is positive m. So negative m multiplied by 0 is 0. So the numerical coefficient here is 0. So we will subtract positive m with it. So 0 minus m is negative m. Next, for the column of x sub 5. 3 and 0 is 0. Okay? So negative m and 0 is 0. So negative m and negative 1 is positive m. So the numerical coefficient here again is 0. So 0 minus positive m is negative m. Okay? So next, for the column of a sub 1, negative 3 times 1/5 is negative 3/5. Plus negative m times negative 1/5 is positive 1/5. Plus negative m plus or times negative 1/5 is equal to positive 1/5 m. Okay, so we will just add them, and the sum we will use to subtract from the numerical coefficient here, which is negative m. Okay, so the resulting value is negative 3/5 m plus 3/5. Okay, so next, for the column of a sub 2, negative 3 multiplied by 0, 0. Negative m multiplied by 1 is negative m. Next, negative m and 0 is 0. So we will subtract the negative m from the numerical coefficient here, which is negative m. So negative m minus negative m is equal to 0. Next, for the last column of a sub 3. So negative 3 multiplied by 0 is 0. Negative m multiplied by 0 is 0. Negative m multiplied by 1 is negative m. So subtract it from the numerical coefficient here, which is negative m. So negative m minus negative m is equal to 0. So we will just leave the computation of RHS to this 3 dash because we still have the artificial variables here under x sub b or in the solution. Okay. So step 4, again choose the variable with the highest positive value of Cj minus Cj. So what is it? So the highest is 23 over m minus 7 over 7 fifth. Okay. So we will now compute for the theta. So 2 divided by 1/5 is equal to 10. 4 divided by 4/5 is equal to 5. Next for a sub 3, 10 divided by 19 over 5 is equal to 19. 10 over 19 over 5 is 50 over 19. Now we will choose the lowest theta here. So what is the lowest theta here? It is 50 over 19. Okay? So meaning a sub 3 will be replaced by x sub 2 because this column is x sub 2. Now for the third iteration, you notice that a sub 3 is already replaced by x sub 2. So how do we replace it? We will now divide all the elements of a sub 3 here in the second iteration with the pivot element. So this is the pivot element because it is in the intersection, okay, of our chosen column and our chosen row. Okay, so dividing all of the elements here, we will get these elements. Okay, the new row for x sub 2. Now we will think of a way to make a identity matrix between the basic variables that are here. So what are the basic variables? X sub 1, a sub 2, x sub 2. Okay? So first, we rewrite one row at a time. Okay? So we rewrite this row, a sub 2. Okay? So to rewrite that, this value should be 0. Okay? For us to have an identity matrix. So what number should we use to make this element 0? So it is 4/5 because it is the value here in a sub 2. Because when we multiplied 4/5 with positive 1, then it is equal to 4/5. Then we subtract 4/5 from 4/5 here, okay? It will be 0. Okay? So you will do the same process for all the elements. Okay? Up to the RHS value. Okay? So first, you will multiply 4/5 with the value in this row, x sub 2 row. Okay? Then you will subtract the product to the corresponding previous value of a sub 2. And the result will be placed here in the new row of a sub 2 up to RHS. Okay, so you will do that up to RHS. Next, for x sub 1, so what is the value for us to have an identity matrix? This element should be 0. So we will use, what is the value in the previous iteration? It is 1/5. We will use 1/5 here as our multiplier. Okay? Because 1 times 1/5 is 1/5. Then when we subtract 1/5 by 1/5, it is 0. Okay? So you will do that again to all the elements here up to RHS to rewrite x sub 1. So now, the next step is, after you rewrite all the rows, the next step is to compute the Cj minus Zj. Okay? So you notice that the values here become 0, and we only have two positive numbers or positive values. This 1 3 over 19m plus 14 over 19 and 4 over 19m minus 7 over 19. So which is higher among these two? So the higher one is 4 over 19 because it is higher than 3 over 19. Okay, so we will choose this. So what column is this? This column is x sub 5 because this one is x sub 1, x sub 2, x sub 3, x sub 4, and x sub 5. Okay, so we choose the column of x sub 5. Now, we will solve for the theta. To solve the theta, okay, so 28 over 19 divided by 1 over 19 is 28. Next, 36 over 19 divided by 4 over 19 is 9. And this one, we do not evaluate it because our denominator is negative 5 over 19. Okay, so we will choose the theta 9 because it is lower than 28. So meaning a sub 2, row a sub 2 will be replaced by column x sub 5. So for the fourth and last iteration, you notice that x sub 5 is here now. A sub 2 was replaced by x sub 5. Okay, so we replace it by dividing all the elements of the previous a sub 2 here with the pivot element, which is 4 over 19. That's why it becomes 0, 0, 3 over 19 divided by 4 over 19 is 3/4. Okay, so we will do that up to here in the RHS. Then you will think again of the a multiplier that will make an identity matrix between these basic variables x sub 1, x sub 5, and x sub 2. So this value of x sub 1 row should be 0. Okay, so what number can we use? So we will use this, the previous value, the 1 over 19 to make this 0 because 1 times 1 over 19 is 1 over 19. Then we will subtract it from the previous value, which is 1 over 19. It will become 0. Okay, so you will do that for the rest of the values of x sub 1 row until RHS. The next, for x sub 2, to write it, what multiplier can we use? So we can use negative 5 over 19 because it is the previous value here. Okay, because negative 5 over 19 times 1 here is equal to negative 5 over 19. Then negative 5 over 19 minus negative 5 over 19, it will become 0. Okay, so you will do that for the rest of the elements here in x sub 2 until RHS. Okay, so you notice that all the values here in Cj minus Zj are zeros and negative. Okay, so meaning the iteration terminates giving our optimal solution. So for x sub 1, it is equal to 1, x sub 5 equals to 9, x sub 2 is equal to 5. So getting the optimal value, it is 13. Negative 13 here because we will just multiply negative 1 for the optimal solution to make it positive. So it is for minimization method. Okay, next is economic interpretation of the dual simplex algorithm. Okay, so dual linear programming, what is that? It makes advances to the relationship of a given linear programming model primal. So the first given is the primal, okay? And another related linear programming model, which is the dual. Meaning this dual linear programming model is related to this primal model. Okay? In terms of variables, which bring shadow price interpretation. So this shadow price will be interpreted by the variables we will find in the dual, okay? Dual programming model. Okay. So to solve, we have our example 1 this model. Okay, so the objective function is maximize z is equal to 3x sub 1 plus 5x sub 2, subject to these constraints. Okay, so we have three constraints here again. Okay, first, second, and third. Okay, and you notice that the different one is the third because it has a greater than equal sign. Okay, so now this is the rule for the dual programming model. So let the LP model above be the primal model. So we will consider this given as the primal model. Now, to rewrite its dual model, the following rules shall be considered. Okay, this rule is applicable for vice versa, meaning if the dual is given, you can rewrite the primal using these same rules. Okay, so if in the primal it is maximization, then the dual should be minimization. Okay, then if in the primal the variables there are variables, so the variables will become constraints in the dual. Okay, so vice versa, if in the primal it is constraint, it will be variables in the dual. Now for if the RHS in the primal will become objective function in the dual. Vice versa, the objective function in the primal will become RHS values in the dual. Okay, and the matrix. Okay, because what we are doing in the simplex table is a matrix. So matrix A, which is in the table, will become a transpose, a transpose for the dual. Okay, so we will just transpose it. So here for other rules, if the primal is maximization and the dual is minimization, here are the rules. If the constraint in the primal maximization is less than equal, the variable will have a greater than equal symbol for the dual minimization, and it is vice versa. Okay, next, if the constraint in the primal maximization has the sign of equal, okay, meaning the dual minimization will be unrestricted variable. When you say unrestricted, it can be equal or not equal to 0. Okay, so if the variable in the primal maximization is greater than or equal, then for the dual minimization, the constraint will be greater than and equal also. Okay, so vice versa here. Okay, next, if the variable is unrestricted in the primal maximization, the constraint in the dual minimization has the equal sign or restricted sign. Okay, so now let's apply it. The dual of the primal model above is this. Okay, so we got the dual of this primal model by applying all of this. Okay, so minimize. Why this is minimized? Because the primal model is maximized. And here you will notice that these values 60, 120, and 10 are taken from the RHS values or the right hand side values of the primal. Okay, and you'll notice here that this 1, 3, negative 1 are taken from the x sub 1 variables here in the constraint, which is 1, 3, and 1. So why does the positive 1 here becomes negative 1 here? Because as a rule, if the constraint symbol is greater than equal in the primal model, the constraint in the will become greater than equal also. Okay, but the variable will have a negative sign. That's why it is negative 1 here. And you also notice that instead of using x as our variable, we used here y, okay, for us to easily determine what is the primal and what is the dual model. So our primal model here is represented by x variables, while our dual model here is represented by y variables. Okay, so here we got 3 and 4 because it is from here, the variables of x sub 2, or the coefficients of x sub 2. And these RHS values are from the coefficients of the objective function of the primal model, which is 3 and 5. That's why it is 3 and 5 here. And now for the negativity constraints. You notice that y sub 1 and y sub 2 are less than or equal to 0. So these values will be less than or equal to 0 if in the primal model the two constraints, the first constraint and second constraints, have the sign of less than or equal. Okay, so you notice here that y sub 3 is greater than or equal to 0 because the third constraint here has also the sign of greater than equal. So you will just look on the primal model for the sign of this constraints. Okay, so here we will accept negative values of y sub 1, y sub 2, but we will only accept positive values of y sub 3. Okay, so solving by dual simplex algorithm, we will just add slack variables to our objective function and also to the constraints. Now you notice that we do not use the big M method here because this one is different. It's called the dual simplex algorithm. Okay, we just add slack variables, and you notice that the slack variables here is negative because the sign is greater than equal, and also the slack variable here is negative because the sign is also greater than equal. Okay, so by solving it in the dual simplex algorithm, we will assume that y sub 1, y sub 2, y sub 3 up to y sub 5 should be greater than equal to 0. Okay, for the step number 1, multiply all variables in the objective function constraint 1 and 2 with negative 1. So we will multiply it. That's why it becomes negative 1 here, negative 3, and positive 1, positive 1. And the RHS will become negative 3. Okay? So the same for the second constraint. Okay, we multiply negative up to RHS. Now notice that there is identity matrix between y sub 4 and y sub 5. So here it is. Y sub 4 and y sub 5. 1, 0 and 0 and 1. So it is an identity matrix. So we will use them to start our iteration. Now just leave the optimum value as 3 dashes because of the negative values in RHS. So you will just put 3 dashes if there are negative values in the RHS. Now choose the row with the most negative value. Okay, most negative value in RHS. So what is the row with the most negative value? It is y sub 5 because it is negative 5. Meaning when you say most negative value, it means that the lowest, okay? The lowest value when it terms in negative, okay? Because negative 3 is higher than negative 5, right? So that's what it means, okay? So we will send it out first and choose the column with the smallest, okay? Theta to enter. Okay, so what is the smallest value of theta to enter? So you notice that the computation of theta here is placed here, okay? On the column, okay? Column, it is computed through columns here, okay? So that is the it is a different way, okay, of solving than we used to do. Okay, so this is done in the dual simplex. Okay, so because we have chosen negative 5, okay, row y sub 5, we will now divide the c sub j minus w sub j with the elements here, which is negative 3. So here you also notice that z sub j becomes w, okay, w sub j. So this is for us to differentiate the dual simplex with the normal simplex way. Okay, so negative 60 divided by negative 3, it will become positive 3 or positive 20. Okay, so positive 20, and negative 120 divided by negative 4, it will become what? Positive 30. Okay, so which is lower, positive 20 or negative 30? So the lower one is positive 20. So we will choose to enter y sub 1. So y sub 1 will replace y sub 5. Okay? So we will add rows for the next iteration. So divide the pivot row, okay, by negative 3. So why we divide it? Because negative 3 is our pivot element. It lies in the intersection of our chosen column and our chosen row. Okay? So what is the pivot row? So the pivot row is this, then y sub 5. Okay? Which is now y sub 1 for the second iteration. Okay? So you will just divide all of this with negative 3. Okay? So it will turn out like this. You will do that up to the value of RHS. Okay? Then we will just get the identity matrix between the basic variables y sub 4 and y sub 1. So what is the multiplier we can use to make this value 0? So the previous value is negative 1, so we will use that number. Okay? Because 1 times negative 1 is negative 1. So negative 1 minus negative 1, it will become 0. Okay? So you will do that for the rest of these numbers up to the RHS. Okay? Then next step, we will just do the steps in the step 1. Okay? So now we will choose the row with the most negative, which is this. Okay? Row y sub 4. Okay? Then we will compute for the theta here. So to compute for the theta, you notice that there is already the values of cj minus wj. So I know you already know how to compute this, okay? Because you will just multiply these values of c sub b with this one, okay? Then add them, then subtract them from these values, okay? So this is negative 40 because negative 60 times 4/3 is equal to negative 80. So negative 120 minus negative 80, it will become negative 40. That's why it is negative 40 here. Okay? So for the computation of theta, you will just divide these values of c sub j minus w sub j with the corresponding elements from our chosen row. Okay? So negative 40 divided by negative 5/3 is equal to positive 24. Okay? And negative 10 divided by 1 is negative 10. Okay? So now we will choose the column with the least value. So what is the least value here? So the least value is negative 10. Okay? So we will enter y sub 3. Okay? It will replace our chosen row, which is y sub 4. Okay? So that's why in the next iteration, y sub 3 here replace y sub 4. Okay? Then to replace it, you will just divide all the elements in the y sub 4 row in the previous iteration. The pivot element here is 1 because it it lies in the intersection of the chosen row, which is y sub 4, and the chosen column, which is y sub 3, because it has the lowest value of theta. So meaning in the next iteration, y sub 4, row y sub 4 will be replaced by the column y sub 3. Okay, so in this next iteration, y sub 4 was replaced by y sub 3. And you notice that all the elements here are just the same, because when we divide each element by the pivot element 1, it will be the same. Okay, so next, you will rewrite y sub 1. Okay, you will make an identity matrix between y sub 3 and y sub 1. So this value should be 0. So what should we use? Okay, so since the previous value is 0, we will just use 0 as our multiplier. And when we use 0 as our multiplier, all the elements will be the same. Okay, up to RHS. Now, let's compute Cj minus W sub j. Okay, so negative 10 times negative 5 over 3 plus negative 6 times 4 thirds. Okay, so their sum will be subtracted from here, negative 120, and the result will be positive 34. Okay, so this will be negative 10 times 1, so negative 10, negative 60 times 0, 0. So it will be 0 here. Okay, then you will compute it up to y sub 5. So now we will just repeat the step 1 and 2. We will choose the row with the negative RHS. So this one, y sub 3, because it has negative 4 thirds RHS. And we will select the lowest theta. So the lowest theta is 10. So meaning row y sub 3 will be replaced by column y sub 4. Okay? So the next iteration, we will divide again all the elements here in the previous iteration with the pivot element. So what is the pivot element again? It is 1, because it is in the intersection of your chosen row and column. So if it is 1, just rewrite all the previous values here. Okay, so next you will make an identity matrix between y sub 4 and y sub 1 again. So what should you use to make this value equals to 0? So since the previous value is 0, you will use the multiplier 0. And by doing that, you will just copy paste all the elements here again. Okay, just the same. Then you will compute for the Cj minus Wj. You notice that the values of Cj minus Wj here is the same with the second iteration, but the computation for Cj minus Wj will be different. So the lowest value here is negative 20. Okay, so you will choose column y sub 5. So it will replace the row y sub 4. Okay, so here in iteration 5, we write it down, okay, by dividing all the elements or values here in the previous row, which is y sub 4, by the pivot element. So what is the pivot element? The pivot element is negative 1/3, because it is in the intersection of column y sub 5 and row y sub 4. So when we divide these elements up to RHS by negative 1/3, you will get this. Okay, for the row y sub 5. Now you will make a identity matrix between these basic variables y sub 5 and y sub 1. So this value should be 0. So what is our multiplier to make this value 0? So the multiplier is negative 1/3, because it is the previous value of the corresponding cell of y sub 1. Okay, so you will multiply the element here in the y sub 1 by negative 1/3, then you will subtract the product to the previous value, okay, of y sub 1 to rewrite the new y sub 1 for the fifth iteration. Okay, so you will do that until to this RHS. Okay, so now you will compute for the Cj minus Wj. Okay, so to compute, we'll just multiply again one by one, then add, then subtract to these values. Okay, so you will get these values. Now notice that the RHS values are positive. Okay, they are positive now, 4 and 3. Thus, choose the row with the higher value of RHS, meaning we are doing now the simplex way because we have positive values already. Okay, so by doing the simplex way, we will choose the higher value, which is 4. Okay, and now also in simplex way, we will choose the theta with the lowest positive value. So what is the lowest positive value? It is 20. So we will not choose 0 because we will just choose positive, not equal to negative or 0. Okay, so the lowest is 20, meaning row y sub 5 will be replaced by column y sub 2. Okay, and the intersection or the pivot element of them is 5. Okay, that's why in the next iteration, iteration 6, you notice that we divide all the elements here by 1 and we put them here. Okay, so 0 divided by 5 is 0, so 5 divided by 1 is 1. So you will do that until RHS. Okay, then you will again make an identity matrix between these basic variables y sub 2 and y sub 1. So what is the multiplier for this to become 0? So the multiplier is 3 because it is the previous value. Okay, so you do that until RHS. Now, in minimization method, just multiply the negative 1, multiply with negative 1 the optimal value because this is negative to make it positive. Okay, because all the basic variables y sub 1, y sub 2, okay, are equal to 0. The Cj minus Wj of these basic variables are equal to 0. Okay, and the Cj minus Wj of the non-basic variables, which are these, are negative values. Okay, they are negative values here, negative 82, negative 72, negative 12. So no variable can be entered anymore. The iteration will terminate. So giving this best solution, y sub 1 is equal to 3/5 and y sub 2 is equal to 4/5 with the optimal value of 132. So notice that the dual model yields the same optimal value as with the primal model, which is 132 tons of finished products, because it is the same with this. Okay, this iteration we used in simplex algorithm. Okay, so you notice that it has also 132. So it is the same with this dual simplex solution. Okay, but the thing is, the resulting set of dual solution, first is y sub 1 3/5 and y sub 2 4/5 and y sub 3 0. So why do we have y sub 3 as 0? Because y sub 3 is not indicated here, meaning it is already equal to 0. Okay, so those solutions are called the shadow prices or marginal values of each given resources, meaning y sub 1 is the shadow price or marginal value of constraint 1. Y sub 2 is the shadow price or the marginal value of constraint 2. And y sub 3 is the shadow price or the marginal value of constraint 3 at the optimum. Okay? So what does it mean? This means that 1 ton, okay, 1 ton of constraint 1 is equal to 3/5 number of manpower in machine. Okay? So that is the equivalent. And 1 ton of constraint 2, okay, is equal to 4/5 number of manpower in machine. Okay? Do you get it? Because they are the equivalent. Y sub 1 is for constraint 1, y sub 2 is for constraint 2, and y sub 3 is for constraint 3. Okay? Also, if constraint 1 is increased by delta or a small amount, okay, of ton, so when you increase constraint 1 by a small amount of ton, okay, then the optimal value will go up by 3/5 delta, okay? Meaning, how much you add or how much is that small amount you add in the constraint 1 will increase the optimal value by this, okay? 3/5 times the amount you increase. Okay, do you get it? The same with the constraint 2, which is 4/5 times delta. Okay? However, one cannot increase constraint to a big amount as it will result to another model. So, remember that. You cannot increase the amount for each constraint to a big amount because it will result to another model. You can increase it by a small amount only. Okay? So lastly, y sub 3 is equal to 0. So what does it mean? It means that the slack variable is in the primal solution. Okay? So which is true? Because we have a slack variable with a solution x sub 5 is a slack variable with a solution of 14, which is in the primal problem. So when we go back to the simplex way of solving that, you notice, so remember, we have x sub 5 is equal to 14. Okay? So, that is what is being implied by the y sub 3 equals to 0. Okay? Meaning, it means that constraint 3 is not fully utilized. Okay? So, while constraint 1 and constraint 2 are fully utilized, constraint 3 is not fully utilized. Okay? By the presence of the slack variable, which is 14. Okay? So thus, its shadow price or marginal value is 0. So you remember that if a constraint is not fully utilized, the equivalent shadow price or marginal value will be equals to 0. So here is another way of finding the dual solution of LP model. Okay, just by looking the values of C sub j minus Z sub j in the last iteration. The last iteration of the simplex way. Okay. So consider the last iteration of example 1, maximization of the primal model. Yeah, you notice that the C sub j minus Z sub j values of non-basic variables, so what are the non-basic? X sub 3 and X sub 4, okay? Represent the dual solution of the problem. So it is the same with the dual solution of the dual simplex way. So X 3/5 and 4/5, okay? So it is the same. So this one is equivalent to the y sub 1, this 2 is equal to y sub 2, and this one is equivalent to y sub 3. So it is more easy to use. You can just refer to this to find the dual solution, and you can save your time by not doing the dual simplex way, because in the simplex way you can easily find it already. Okay, the values of the shadow prices are the marginal values. Okay. Next, the following last iteration is from example 2. Okay, minimization. So here, the C sub j minus Z sub j values of non-basic variables x sub 3 and x sub 4 represent the dual solution of the problem. Okay, so there it is. Okay, negative 1/4 or 1/4, okay, is the equivalent of y sub 1 here for the second problem, and 7/4 is the equivalent of y sub 2, and y sub 3 is equal to 0. Okay, so why it is equals to 0? Because again, you notice that there is a slack variable present in the solution, so that's what it implies. Okay, now using Excel solver method for example 1 problem primal model. So now open your Microsoft Excel. Okay, now write this table. Okay, so you can write your table in the way you want it to be, just to emphasize the solution and the optimal value. So the number 1 example is to maximize the number of manpower and the number of machine. Okay, so the resulting solution will be the number of man and machine to be added. Okay, so tons per manpower machine. Okay, so here are the equivalent of tons per manpower in machine. And this is the optimal Z. This one is for constraint 1, constraint 2, and constraint 3. So these three are different processes, as you recall in the problem. Okay, so these are the coefficients of those constraints. So here you will see the utilized tons of the raw materials, okay, of the target tons. So here you have a formula, okay. So the formula for the optimal Z is just the sum of the product of this one and this one, and the product of this one and this one, okay. Next, the formula for this first row of the utilized tons of Fg is just the product of this one and this one plus the product of this one and this one, okay. So it is the same with the following formula, okay. So the product of this one and this one, the product of this one and this one, okay. So you notice here that my formula is in $sign, meaning it is I press F4. So after I click here in the number of manpower and number of machine, I press F4 so that I can drag it to the last row, okay. Because when you do not press F4, it will not be a correct formula. So let's do the formula. So it is equals to this one. So you click or press F4 and times, okay, times this plus this one, then click F4 and times this, okay. Then just drag it down here, okay. Drag this down here, okay. So you have it, your formula. So the next thing you do is go to data again, data, and click solver. So this is the solver, okay. Then for the set objective, so if there are data here, you can reset all first, okay. Set all to empty all the data. So for the set objective, you will click here and select this cell, so this one, okay. So click that and select this one. Then for since it is maximization, you should select this max, okay. Then by changing cell, you can click this and select this, okay. Then for the subjects to constraint, click add, okay. Click add, and for this cell reference, click this and the corresponding sign. So the sign for the first constraint is less than equal. So here you will click this one, okay. Then you will click add, and for the second one, click this, and the sign for the second constraint is this, less than or equal again. Then for this one, it is equivalent here, okay. Then click add. Then for the last one and for the third one is this. Then the sign for the third constraint is greater than equal, okay. So you must change it, and for this constraint you select this, okay. Then click OK. So notice that you already have these three constraints. Then make sure that the make unconstrained variables na negative be checked, okay. And select Simplex LP. Then click solve and click OK. Solver found the solution, so click OK. So now you have your x sub 1 is equal to 24 and x sub 2 is equal to 12, okay. Now for the example number 1, dual problem, okay, the dual problem of the example number 1. So this is how you do it. So in the Microsoft Excel, you make your table again, just like this. Okay? So again, after you make your table, you will just click solver, data, then solver. Okay? Then you can reset all here. Then for this one, click this and choose this one. Okay? The optimal Z. And since this is a minimization, click this, min. Okay? And by changing variable cells, click this one. Okay? Then for the subject to constraints, click add. For the first constraint, for the cell reference, select this. Okay? And the sign is greater than equal for the first constraint. Okay? Then the constraint here is this. Okay? Then click add. And for the second one, second constraint, select this. Then it is the same. The sign is the same. It will be greater than equal also. Okay? For this, select this. Then click OK. So now, make sure to check this and select Simplex. Then click solve. Then solver found a solution. Okay, all constraints and optimality condition are satisfied. Okay, so okay, so click OK. See here for the shadow price. Okay, of the constraint 1, you have 0.6, or it is equivalent to 3/5. Okay, and for the shadow price or the marginal value of the constraint 2, you have 0.8, or equals to 4/5. And the shadow price or the marginal value of the third constraint, it will be equals to 0. So it is the same. Okay, it is the same with the one you solved using Simplex method. Now for 5.0, we have matrix method for LP problems. Okay, so although Simplex method is just similar with the matrix method, okay, because in Simplex we are putting them in a table wherein they are also forming a matrix. But there is also another method called the matrix method. Okay, so let's do that. So for example 1, okay, of the primal model, the example 1 in module 1. So this is the example 1 for module 1. Okay, remember this. So this is the objective function with the slack variables, and the subject to constraints with the slack variables also. Okay, so to recall, the optimal solution here is x sub 1 is equal to 3, x sub 2 is equal to 4, and the optimal value is 1900. Okay, next, from example 1 of module 1, okay, the dual model of that is this, minimize. So you will just make this one as the dual model, okay, with the subject to constraints. So if you solve that, you will have your optimal solution is equal to y sub 1 equals to 100 over 3, y sub 2 is equal to 50. And the optimal value should be the same, which is 1900. Okay? Now, for the matrix notation. So this is the matrix notation. X raised to b is equal to b raised to negative 1 times small letter b. So what is x raised to b? X raised to b is the basis forms or set of basic variables in the primal. Okay? Then b raised to negative 1 is the inverse of the set of basic variables. And lastly, small letter b is the set of RHS value. Okay? The next one, you have y is equal to c sub b multiplied by b raised to negative 1. So, what is y? Y is the corresponding solution to the dual. Okay? So now let's solve the above model using this matrix notation. So we will use this notation first. Okay. So first you have your matrix of the coefficients of the constraints. For constraint 1 you have 3, 3. For constraint 2 you have 4, 3. Okay. So since b here is raised to negative 1, we will get the inverse of this. Okay? Then we will multiply the inverse of that by small letter b. So what is small letter b again? They are the set of RHS value. So these are the RHS value, or the right hand side value. So it is equal to, so how do you get the inverse? So you should already know that in your advanced mathematics. Okay, but as a review, these are the steps in finding the inverse. First, you will get the transpose of the matrix. Okay, then you will find the minor, okay, of each element in the matrix. So you should have known how to find the minors. Okay, so if you solve the minors of each element in this transpose matrix, you will have this. This is called matrix of minors of a raised to t. Okay, so this is just the review of the steps in finding the inverse. Okay, so after you get the matrix of minors of the transpose matrix, you will get the ADJ of A, meaning you will get the adjoint of A. So how do you get the adjoint of A? You will impose the place sign. So what is the place sign? Right here, positive, negative, positive. Then for the second one, you will multiply negative, positive, negative. And for the third one, you will multiply positive, negative, positive. Okay, to get the adjoint. Then lastly, you will multiply the reciprocal of the determinant of the original matrix. So the determinant of the original matrix, you will get its reciprocal. Then you will multiply it to the adjoint matrix, okay, that you get. So after you multiply it, you will get the inverse of it. So this is just a review of the steps in finding the inverse. Okay, so these are not the given in the problem. This is just for reviewing the steps. So if you do that, you will get this matrix. This is the inverse of the 2 by 2 matrix, 3, 3, and 4/3. Okay, then you will multiply it with these values. So how do you multiply a 2 by 2 matrix by 2 by 1 matrix? Okay, so you will multiply by the rows of the first given matrix and the column of the second given matrix. That's why you have negative 1 multiplied by positive 21 here, and positive 1 multiplied by positive 24 here. Okay, and the next, you will multiply the next row with the column of the other matrix. So 4/3 multiplied by 21, then negative 1 multiplied by positive 24. Then that will give you, okay, so after multiplying this, you will add them. After multiplying this, you will add them. It will give you 3 and 4. Okay, so it is the same, 3 and 4. The solution for x sub 1 is equal to 3 and x sub 2 is equal to 4. Okay, so it is the same with this solution. Next, the inverse of a 2 by 2 matrix is this. It is shown here how we find out the inverse of the matrix. So how do we come up with this negative 1, 1, 4/3, and negative 1? Okay, so you can refer to this. Okay, so this is another illustration of the steps. So here, what is B adjugate? Okay, so the adjugate of matrix B. So the adjugate is just by applying the positive and negative sign symbol. So here, we will multiply positive 1. Here, you will multiply negative 1. That's why it is 3 and negative 3. So here, you will multiply negative 1. And here, you will multiply positive 1. That's why it is negative 4 and positive 3. Okay? And here, 1 over B determinant. So the determinant of this matrix. So since this is just a 2 by 2 matrix, to get its determinant, you will just subtract the product of 4 and 3. So this one, the diagonal 4 and 3. Subtract it from the product of another diagonal, which is 3 and 3. Okay, so that's how you get it for a 2 by 2 matrix. Okay, then just multiply it 1 by 1. So 1/3 multiplied by 3. Okay, so next negative 1/3 multiplied by negative 3. Okay, So the result will be like this. So that's how you get your inverse. This is another way of getting the inverse of a matrix. Next, for the corresponding solution to the dual, we will use this formula. Okay? So here the C sub b, or the coefficients of the variables in the objective function, so they are 300 and 250. Okay? You will multiply it with the inverse of b. Okay? So we are already got the inverse of b, which is this. Okay? Then to multiply it, you will multiply it by row times column. Okay? So each one. 300 multiplied by -1 plus 250 multiplied by 4/3. Then for the other one, 300 multiplied by 1, then 250 multiplied by -1. Okay? So you will have there 100 over 3 and 50. So here are the dual solution. Okay? The solution for the dual of the primal problem. So x sub 1 is equal to 100 over 3 and 50 to the x sub 2. Or for the dual, we represent y sub 1. Okay? Instead of x sub 1, we use y sub 1 and y sub 2. Okay? Remember? Now for the post-test, okay? So same direction. So this is just the same with the direction in module 1. Okay? So first you will formulate the linear programming model. So here you will have a dual, okay, programming model. So instead of just getting the primal, you will make the dual of that problem. Okay? Dual model. Okay? So for every problem, like for example in this problem number 1, you will get the primal model as well as the dual model. So for number 2, again, you will make the primal model and the dual model for the number 2 problem. Then for letter B, you will solve the LP problems above, 1 and 2, using algebraic solution. Okay? So in letter B, you will just solve the primal model for algebraic solution. You will not solve the dual. Next, letter C, solve the 2 problems above using graphical. Again, you will just solve the primal. Okay? You will not solve the dual. Next, in letter D, you will solve using simplex algorithm. Now you will solve by primal and dual. Okay? So in letter D, you have 2 answers. Okay? So you have 4 answers because you have primal and dual for each problem. So it is 4. Okay? Next, for letter E, solve the problem above using Excel solver. So you will solve both primal and dual in the using Excel solver. Then last, letter F, solve the following LP problems using matrix method. Okay? So you will use matrix method to get the primal and the dual solution. Okay? So it is 1 and 2. Okay? So final requirement, a one-on-one interview between the teacher and each student to be done if validate the course submission are really done by the learners. Okay?